Okay, here is our triangulated surface model. The first thing I'm going to do is I'm going to detect the holes in this component because I don't want to machine the holes while I'm doing the milling operation. I'm going to drill those items later. So select the triangulated surfaces folder, and either from a drop-down menu or from a toolbar, detect holes. The result of clicking OK to this is to present us with a detected holes plan. Next option is to select that detected holes plan, and then from the geometry drop-down menu, click on Cap Holes. A couple of options here, one for planar holes and one which will follow the contour of the hole edge on the surface. The result of that is to give us a set of circular patches, and they cover the tops of each of the holes and also the bottoms. Next, I need to consolidate and combine these two sets of triangulated surfaces. Select the original model, select the capped holes, right mouse click, option down here, combine folders. The result of that is this folder here. This contains the consolidated model elements. Next thing I want to consider is the size of my stock. I am going to assume that the material supplied has already been profiled. I selected the surface at the bottom, created a silhouette boundary. I had some circular elements and some other bits and pieces that then need to be deleted from that list, just leaving me with the outside boundary item. If I take that outside boundary item and go to geometry, I can then create a prismatic stock model. So this is a representation of the stock that's going to be presented to me for machining. The next thing to consider is how are we going to hold it. I've opted to put 3 clamps onto this component, one here on the left hand side, one at the top right and one at the bottom right. And to do this I have created 3 rectangular silhouette boundaries that are just very slightly larger than the clamps that I'm going to use. We now need to create some more model data from that. So I have my 3 rectangular boundaries, but I need to create some physical 3D geometry from that. So the first thing I need to do is to select the 3 silhouette boundaries and convert them to curves. This is done by the curves drop-down menu and the option at the bottom. The result of that are these silhouette converted curves. Next thing I need to do, I need to create a rule surface from them. So select the curves, geometry menu, ruled surfaces. You'll see here we have direction arrows as to which way the surfaces are going to be offset. So I need to offset them in the Z axis. And my clamps are going to be 35 millimeters tall. By clicking OK to this dialog, I get 3 ruled surfaces. Finally, I want to put a cap on the top of those so I can use either the silhouette boundaries that I had or the silhouette curves. Again, geometry menu, planar patches, and specify the height that I want those patches to be created at, 35 millimeters in this case. The result of that are triangulated surfaces 7. These now need to be combined yet again. So select my main model data, which has got my capped holes in them as well. Select the ruled surfaces and the triangulated surfaces that represent the caps on the top, and again right mouse click, combine folders. The result of that is this group here, and if I open that folder you'll see it consists of the combined triangulated surfaces 2 plus the cap holes, the ruled surfaces, and these triangulated surface patches on the top of the 3 clamps. So this is now one complete model unit. That's got our preparation done. We now need to start on the machining. So let me just open this folder here, and you will see that I'm using the combined triangulated surfaces 9, which is what's visible on the screen at the moment, and I'm also limiting it to the edited silhouette boundary 5, which was what I used to create my stock from. If we look at the area clearance passes and look to see how they were created, I was offered a 63.5 diameter shell mill in order to start to rough this part out. So this is specified here. It does not have a corner radius. If we look on the passes page, material thickness left on of 1 mm on X and Y and 1 mm on Z. The top surface of this component is at Z0, so my max height needs to be edited to 0 here. The tolerance has been degraded because we are roughing, and I've opted for an 8 mm step down. I've also enabled adaptive step down to ensure that I get as low as I possibly can and hit my material on target. So there we can see area clearance roughing toolpath. It is also going to take material out of this central section. Once the passes have been created, the next stage is to link them together. I'll just very briefly animate the first part of this toolpath so you can see what's going on. So it's taking a section out of this triangular middle section now. Once it's completed that, it hops over to all of the other areas that need to be considered. So the result of that area clearance toolpath with the 63.5 cutter is to present to us a stock model looking like this. So the turquoise surfaces on the top are surfaces that have not been touched. The purple is where our 63.5 diameter cutter has been able to get. The next thing to do is to do a rest roughing operation, because we now need to work with a series of smaller and smaller tools. So the next tool that was offered is a 25 diameter cutter. Again, we're using a 1 mm thickness on that. I selected the silhouette boundary and the area clearance toolpath. I was then able to do a rest roughing operation. Here I can specify my new tool. The tool that I chose is this one here. So I have a 25 mm diameter tool, flute length of 50 mm, overall body length of 75. On the passes page, X and Y and Z thicknesses are still at 1 mm. My max height is at 0. I've opted here for a 5 mm step down and also checked the adaptive step down option. So this is going to take more material out, but where we've already roughed out with a larger tool, we're only considering the corners. Stock model 3 represents our area clearance toolpath and our rest area toolpath. So surfaces that you see here in purple were created by the 63.5 diameter cutter. The terracotta type colour here was created by the 25mm. Here is the first stock model. There is a second stock model. Moving on again, selecting both the area clearance toolpath, holding the control key and selecting the rest area clearance toolpath, I can do rest roughing. So I'm now doing a third rest roughing operation. If we look at the parameters for how that was set, then what I've used here is an 8mm diameter tool. Its flute length is 30mm, its body length is 50. I can't guarantee that this is going to clear my clamps, so I've incorporated a tool holder onto the back of it as well to ensure that once I get deep into these pocket areas, if my holder is going to hit anything, it will be protected. There's the third area clearance toolpath, and if I show you the stock model for that, let's switch on all the stock models. So this is where we started from, our first cut. There's our first two cuts, and then finally a stock model that incorporates our 8 diameter cutter, represented here with green. So after using area clearance toolpaths to rough this component out, the first of my semi-finishing passes is to create a waterline toolpath in this central section in order to finish this up. I selected the underside of this surface again, created a silhouette from it, and this time I just retained the silhouette for this central triangular section. By selecting my combined triangulated surfaces 9 item and the edited silhouette boundary, I was then able to create waterline passes just within this boundary. I use a 25mm cutter again, and on my passes X and Y, Z are set to 0 for thickness. My top height of my job is set at Z0, and I've opted for a 4mm step down. To take a spring cut around that, I then created a second waterline pass, which consisted of just 2 profiles. So exactly the same setup as I had before, but this time I said that my step down was 32.5mm and that my minimum height of my component was 65, so that's going to give me 2 passes. Here you can see the 2 passes, they've been linked together. Next task, skim over the top of the job. Core horizontal area toolpath. The elements that were used for that: triangulated surfaces 9, as we see here on screen, and the combined silhouette boundary folder that we have. Back to our 65.3mm shell mill, XY thickness of 1, skin thickness on Z at 0, and just ensuring that I just take material at the top of the job. So I've added a plus and a minus value to my nominal Z0. Waterline toolpath with a 10 by 5 bullnose tool. So what we're trying to achieve here is we're trying to get rid of the terraces and the steps that were put in because of our area clearance paths. So a waterline toolpath with a ball nose tool, and leaving that with a stock thickness of 0.15. 10x5 ball nose tool holder on the back of that. On the passes page, X, Y and Z thickness is set to 0.15. This is a semi-finishing pass, not a finishing pass. I want to address the near vertical walls and relax it to an angle of 45 degrees. I don't want to be machining across flat areas or shallow areas with a ball nose tool using a waterline toolpath. So 45 degrees of incline up to 90 degrees for the steep walls. Adaptive step down is switched on. Step down value is set for 1. Once they've been linked, a brief animation. Here's my tool and tool holder. Finally, deal with the more shallow areas using raster toolpaths. So, to set that up, same tool as we had before, it's a 10x5 cutter. On the passes page we have the same thickness. I've put an angle of 0.01, so this stops it machining the horizontal, the flat areas. Our previous waterline toolpath came down to 45 degrees, so our raster passes need to go up to 45 degrees. I've told it that I'm going to have a step over of 1 mm, and the angle of approach to this component is going to be 90 degrees to the x-axis. So if we look closely in here, you'll see that my toolpath is running top to bottom. We could have a look to see what material has been removed by the series of cutters so far. So I can select the 3 area clearance toolpaths, I can select the waterline toolpaths, the core horizontal, the waterline and the raster. And if I create a stock model from those elements, put that back into the list just here. This is the state of play after 8 toolpaths, where you see 2 colours that shimmy together like this. That indicates that the stock model and the surface model are coincidental, so there's no material on there. Areas where there is dense colour, in this area here, is where we still have material to be removed. We're now starting to finish the part off, so my thicknesses are now set to 0. I created a waterline toolpath using an 8x0 cutter. On the passes page, my thicknesses are now set at 0. I've got an overall step down of 1.5 mm because I'm just doing the near vertical faces. My angle is set between 98.5 degrees and 90 degrees, so I'm only going to do the vertical walls. Any taper beyond half a degree won't be recognized. So here we're just machining the vertical walls. Now, an interesting thing going on just here. Because of the length of my cutter and the holder that I'm using, there would have been a collision between my tool holder and this clamp. We don't allow tool collision, so we have not machined this area here What we would need to do is we would need to remove that clamp, relocate it, and then finish that piece of surface geometry off with a second pass. So I've done the vertical walls. Let's do the horizontal faces now. So an 8mm cutter, just coming into these flat areas, these flat pocket areas. See how the cutter is avoiding that area there. Right, now I'm dealing with the areas that have slope and taper to them. So, using a ball nose cutter, waterline toolpath. Thickness is set to 0. My angled limits, so 45 degrees off the horizontal up to 89 degrees means I won't touch the surfaces that I've machined previously. Step down here is set to 0.5 mm. Because it was set to 45 degrees, there were some areas at the tops of these heel locks that didn't get machined. So in order to do that, I used the new UV machining type toolpath. Let me just briefly show you how that works. So if I take the combined triangulated surfaces and we'll look at this surface here, I need to select that surface, and from the toolbar I can then tell it to build a UV surface. So I selected I think there's probably 5 or 6 of these surfaces at the top. I'm just going to choose one of them to show you. The yellow line defines the flow line direction and the green defines the step over. So if I want to machine this along its length, I need to switch these around. I have an icon button here to do just that. So we'll switch those around. So now my flow line of my cutter will follow the yellow arrows and it will step up along the green one. So because of the direction of the arrow, it's starting at the bottom and will go to the top. Next thing to do is to pick the UV machining option, specify the tool that you're going to use, set any thicknesses that need to be adhered to, and specify a step over. The result of that on all of these other surfaces was to give me this. Brief animation, spin that around. So just single surface machining here, backwards and forwards, following the UV parameterization of the surface. Finally, I needed to deal with all of the shallow areas in this component. So, raster toolpath using our 10x5 cutter. Thickness is set to 0. 0.01 at the base angle, so that avoids doing the flat horizontal faces. Up to an incline of 45 degrees, so it matches and marries up with the waterline toolpath. So running top to bottom on the job. Area clearance toolpaths for these features here, and for the 4 little chambers that run out of the side of the job, and over here as well. So I created a set of silhouette boundaries just by selecting the surfaces and creating silhouettes from them, and then using those silhouettes to machine. So I did area clearance tool passes with a 4mm cutter to clear this out and these items at the back. UV machining on those. And then finally, to finish off these 2 little pockets over here, I did waterline machining. I had adaptive step down checked, and I set my profile step in value to be the same here as I've got on my step down value. That concludes the milling part of this job. If I take my overall boundary and if I select all of my toolpaths now in order to create one final stock model, so this is the result so far. To finish this job off, let's now look at the drilling of the holes and the cycles that are involved. So we want to be working with our original triangulated surface data without the holes in it, and we don't need the editable boundary either. We already have detected those holes, so we can create a drilling folder from that. I only want to look at the holes from the top, so with an A, B and C rotation of 0. Switch those off. If I want to spot drill all of these holes at the same time, then I need to select this drilling data folder. From my toolbar, I can select spot drilling. The system has detected that there are data folders with different composite hole shapes. I'm only interested in spot drilling at the top, so I can OK this message. It's going to use a 6mm diameter drill, which is the diameter of my smallest hole. So that is fine. I am going to increase the tip angle to 90 degrees because this is a spotting drill. On the cycles page, I'm going to change my depth because obviously I don't want to drill to 55mm, so we'll put in a 2mm depth and click OK. Right mouse click, link these passes, a brief look to see what's going on. Here we can see our drill just spotting away there. Right, I'm not going to go ahead and drill all of these, but I'm going to pick out two different types. I'm going to pick out a through hole, and I'm going to pick a through hole with counterbore. Switch all of those off. Through hole, 16 diameter hole, 40 millimeters deep. So we've got holes up here. If we open that folder up, you can see how many holes there are to drill. 1, 2, 3, 4. Select it, right mouse, deep drilling, 16 millimeter diameter drill, 118 degree tip angle. We want to drill all the way through. It's not a blind hole, so we need to have the depth adjustment set. That's going to go an extra 4.8 millimeters through. If I look on the cycles page, then I've got a drill depth of 40. I'm going to start at the beginning of part 1. Right mouse click, link. We'll animate that. And if we look at these holes here, counterbored holes, let's drill them first. So deep drilling. Now if we look on the cycles page, you'll see we now have two elements. The first element being the counterbore at the top. The second element is the remaining part of the hole. The remaining part of the hole is 22 millimeters diameter. Come back to my tooling, change this to 22 millimeters. Add the depth adjustment and click OK. Right mouse click, link passes. There's our deep drilling cycle. Let's use that one again. Only this time we'll do bore milling. Specify a tool. We'll have a 10 millimeter tool with no corner radius. It's picked this up from the depth of the hole. We're only doing the counterbore at the top, so 20 millimeters is probably going to be sufficient. If I now look at the cycles, we can still see the two elements here, but I want to start at part 1 and I want to end at the end of part 1. Its diameter is 25 millimeters. Peck depth, let's take this in one shot, 5.7 millimeters. Right mouse, link the passes, and let's animate that. So the next one's going to be over here, round the part, one profile, and done. I hope this has been of use to you, and please contact me if you have any questions or queries. Thank you very much.